weiß ich nicht, I don't know.
Okay, so
Thanks for waiting, I guess.
Well, hello and welcome. Today we want to talk about the central question at SCIoI. What is intelligence? With a question mark, not like the poster suggested that we have the answer. But we think we have one important piece, at least, of talking about this question is talking about principles, as I think all of you should be more or less aware, coming from SCIoI. We think one part of answering this question is really, well, finding out these common principles that are common across all these different varieties of behavior, well, the variety of instances of behavior that are intelligent, or that we call intelligent. And this is exactly what we're going to talk about today, principles. And we're going to talk about this by, first of all, going into, well, an historical example of how having principles is extremely useful when doing science. And this historical example is not going to be on the subject matter of intelligence, as you will see in a second. But this is really to illustrate how talking about principles is not just a fun ivory tower exercise, but really something we must do and that will be helpful to all of us to do. And once we've done that, we'll then actually talk about the candidates for principles of intelligence and how having these candidates has already been useful to different research endeavors here. So, before we get into intelligence, let's get into a different topic, a historical topic.
The year is... Wait, when it starts. The year, I'm playing a narrator. The year is 1869. The Edinburgh Seven just became the first female students in UK universities. The first issue of Nature was just published. And most importantly, margarine was just invented. A good year for science, right? But it is about to get better. We turn our attention to the Russian chemist called Dmitry Mendeleev.
Chemical elements everywhere nowadays, but no principle in how they behave. Impossible. There must be something. If I order them like this? No.
Several hours later,
I need to order them by weight. And then there's some repeating pattern in how they behave. Sodium is like potassium, bromine like chlorine. But what is this? There's some hole in my table here between zinc and arsenic. There must exist something there.
Mendeleev calls this pattern the periodic law. And he publishes his new table of elements, including pointers to missing elements. At the beginning, he gets ridiculed.
How useless! A big table proposed.
But then, some of his predictions are true, and everyone was like...
So, as I told you before, we didn't talk about chemistry because we like it so much, even though we do, very important. But because we think it illustrates very well how principles can be or are useful in science. So to explain you that a bit closer, let's actually talk about the context, what happened. Well,
can I just, sorry, is this AI generated? Yeah.
Yes. You can
I was confused about the elements there.
So, in the 19th century, we had about 60 elements, like discovered, roundish, and we could already experimentally determine certain properties of them, like their weight, but also atomic radius, valence. And what Mendeleev found was this very first published table. This will differ a bit to what the table of elements you know. First of all, it is transposed, so these are actually the columns that you might know. Secondly, there seem to be some things off with it, but more on that in a second. The important thing is that he ordered the elements by their weight, these are these numbers, and then certain elements that appear close to each other, that repeat periodically, have the same behaviors. The same properties, like atomic radius, or like their valence. even though they have very varying weights. And what he then found, and what is really the most interesting thing about this, is that there were some missing things that he didn't really know, but they needed to be there according to his principle. And he predicted for them certain weights. And when these elements later have been discovered, actually they were discovered, the most important thing. So these predictions that he made actually turned out to be true. But more importantly, the weights that he predicted for them even were extremely accurate, more accurate than experimental first results for them actually were, as we know, given our modern day measuring devices. And this really shows us how having principles is an extremely helpful thing in science, because it structures the problem space in a way that we can actually inform the experiments we should do based on predictions that come from the principle. But even more, it shows us how having even vague ideas of principles, because this table is completely off on some parts, like this part doesn't make any sense on rare earth elements. The noble gases also were not yet discovered and somehow are missing, and still having a vague idea of principles, even though with errors, already helped progressing science. And not only that, by refining it later, the same principle, just with more observational data, actually it really redefined the whole field of chemistry as we know it today. And this is not a one-off, but instead this is usually how science progresses, be it for Einstein's general relativity theory or the discovery of the Higgs boson, all stem from some notion of principle that gave us the ability to really understand the full research field better. And what we're gonna use the remainder of our talk now, that I hope you believe me that having principles is generally useful to progress science, is to tell you about how having some candidates for principles of intelligence has been actually helpful to our individual research, and then also to some other research across SCIoI. And these candidates for principles that I'm gonna show you, I'm not showing you them now yet, they're gonna be a bit more vague, as I said, maybe even owing to the extreme variety of complex intelligent behaviors compared to the just shy of 118 elements that we know today. So yeah, please bear with us. We're gonna show you how having even these vague principles, these candidates, is gonna be, well, was useful for us. And to start with this, we again want to tell you a little story, even though the main researcher in the story might be a bit less grand than Mendeleev, at least yet. The year is 2022. James Webb Space Telescope just enters orbit and sends us the first spectacular images of our universe. Elon Musk takes over Twitter, and GPT-3 just comes into its most famous form, ChatGPT. Maybe a somewhat good year for science and technology, but it's about to get better as we turn our attention to a young PhD student called Aravind.
Thank you. I'm frustrated now. I'm like, illusions here, illusions there, illusions everywhere. No principle to find how to understand these nasty things. But I guess I'll just start somewhere. I'll just start with this visual illusion here.
After several weeks, Aravind implements a model, but it's not able to make really sense of all the data that Angelica collected in her psychophysical studies.
Right, so the model fits most of the data I see here, so that's good. But there are some few subjects here I'm not able to make the model fit. What do? Maybe I'll just try tuning the model parameters a little bit, try to just overfit this model to these weird outliers.
The modified model began generating very strange outputs, unlike anything Aravind expected to see.
What the heck is this? Maybe, I mean, it serves me right? Because I didn't really follow my good old lessons from computer vision classes. But well, be it as it is, I'll just show it to my group in our next meeting.
In the next meeting, Oliver and Martin are from these random outputs But Angelica really just shrugs and says that like a few study participants actually reported seeing exactly these effects. Then Oliver goes like this, like this, and goes like.
I guess everybody understands this was just a skit loosely inspired from what actually happened. Comedic effect. But the surprising bit was true, though. So, well, not with, I guess, these expressions. Oliver can talk about that. But it was surprising. So, before I talk about that, let me tell you what illusion we happen to start with, visual illusion. Most of you here might have seen this. So I'd ask you to stare only over there at the dot. Don't change your gaze away from it. And right now you've been presented 3 images in sequence. So you have colored star, outlines, colored, outline. And if the illusion is working for you, then, and don't shift your gaze again, keep it at the center. If it's working for you, then these outlines seem to have a faint afterglow, like some kind of an after effect. We call it color after effect. The striking thing about this illusion is that the color of the after effect fits the colors that you saw in the beginning. There's a correspondence between them. So we started with this illusion. So I started to make a model for this, and the model takes this as input, like just as you saw, but a simplified version, just 1 star instead of 2. By the way, 1 star would also work on you. So that would be, let's say, the model input, and then the model percept, or the output of the model, would correspondingly be colored for colored stars, and then corresponding after effects. Now, this is what most people see, and the initial data we did with the psychophysical experiment suggested that. But once we encountered the weird outliers, as I referred to, and I changed the model began to show this as the output. That was one. There was also another one, this one. And yeah, when we saw this, it kind of like seems like not, at least, I mean, I never had this to myself. So it seemed like pretty random output. So, but then what we did was actually confirm this in another psychophysical study. And we found that, as most of you, I guess, would here see, most of you see this, most of the study participants saw that. A fewer number of people see this, and even fewer, actually not statistically significant, see this version. Now, why did we tell you the story, or the skit and all that? So this is just, I guess, an illustrative example of what we do in SCIoI. And again, I have to mention this incident, or whatever we showed, it's nowhere as profound or grand as with Mendeleev. But it has 2 specific overlaps. One, the model was able to predict previously unobserved things. And 2, which is more important for this talk today, our research was guided by a principle, well, a candidate principle. And what is that candidate principle? We call it strong interactions between components. And to explain this, so I guess everybody in SCIoI, we have this sort of implicit assumption that any intelligent creature, artificial or biological, must be composed of several components. And unlike when you want to build a system that way, and unlike in systems engineering, or like when you see large software programs where you design components and then design simple interfaces with them, we suppose that rich and strong interactions help or allow a system to be intelligent. So that's the candidate principle. We can talk about details of this later, and maybe the details will get a little more clear as we go. But I must say, how was this useful to us in the visual illusions? Well, the typical way to approach a model which would try to process shapes and colors would be to, you look at the image input and then you separate in the individual modalities, the independent modalities, the brightness and the color, and then you would process them. So from the brightness, you can extract shape and color here. So, but you see here, I mean, this is how you typically do it. And these are also called pipelines in computer vision or software engineering as well. But you see that even though you separated the information out over here in the beginning, there's still information overlap, right? So the outline of the shape still corresponds to the edges of the color that is being processed. So what we decided to do was interconnect them. We see that there is an information overlap at some point in the pipeline, and this is, again, unlike computer vision, where you separate out all the required things in the very beginning, you filter them out, and then you work on them. But we think that this is a thing with strong interconnections. We add interconnections wherever we see that there may be an overlap of information, because there it can actually mutually benefit each other. The color benefits out of shape, and shape out of color. So with that, we were able to get the similar percept as humans. I mean, I've simplified this to a large extent, but at the big picture level, this is it. The model is it. I mentioned interconnected, so that's interconnections. And one thing I left out was each of these blocks are recursive in nature. Yeah, Leah, you have something?
Yeah, just a quick question. When you say you were able to get percepts like humans, you mean by introducing these connections, you got the percepts that that minority of people got? Is that what
All of them.
Oh, okay.
Because it is, in the beginning, we tuned the model to show the main, the larger set. But then when I refer to tuning model parameters, I changed the time dynamics behavior in the color to try to reflect that, and then suddenly we have new percepts.
I see. Okay, sorry.
So we can take questions, but I guess we sort of intend some of these clarifications to be at the end. It's okay that yes, no worries. But yeah, if you have any immediate concerns, do find out. But otherwise, we'll have a large discussion session at the end. Well, by large, maybe 15 minutes. So yeah, I mentioned interconnectedness and also recursive bit, which is for us to take advantage of just evolution of time. And these two terms might just hint at something Vito and I have been talking for ages, I mean, in other talks, which is interconnected recursive estimators. This is just really an instance of the candidate principle of strong interaction between components. And we might have also referred to interconnected recursive estimators as a programming language, and we meant it in a metaphorical sense. But the important thing is that even though we have this programming language, we are able to express more than we put in the model. So that's the key. And that is sort of relates to the consequence of having strong interaction. So maybe in general, I would be bold enough to say that when you have more components, I guess, yeah, like more components add to them, and then richer connections, the complexity as a consequence is just going to happen. It's an unavoidable consequence, I think, but it's a fortuitous consequence for building intelligent systems. And one thing I should note, because again, I refer to it as programming language, metaphorical, interconnected recursive estimators is not a recipe to create intelligent things, at least not yet. And this is really, interconnected recursive estimators it's ongoing work. We need to refine what we mean by that. We need to apply it on different problems, learn from them, deliberate over the details. And maybe speaking of deliberation, I mentioned two terms, right? Strong interaction between components and interconnector recursive estimators. Maybe some of you might have, maybe the PIs at least, might have been thinking of weak decomposability and functional non-decomposability, because these are sort of older terms that sort of refer to the same concept. Some of these are in the white paper as well. But like when you just stand back and look at them, yeah, they're just different kinds of terms, but all of them are trying to express maybe something, like some kind of intuition about intelligent systems. And it might drive people away from thinking, oh, it's too vague, how can we use it? But like what we are trying to say today is that even though the terms may be vague, it's useful for us to guide our research. And what we really need to do, and which would be sort of the takeaway from the talk today, would be, I mean, we'll be throwing more things at you. We'll be throwing more candidate principles, more ideas. And what we're trying to do really is to try to articulate these intuitions, if I can call them, as clearly as possible. Because when we do that, we will be able to collectively reflect on it, make those concepts clearer, and in turn, and that's the important bit, in turn the concepts help guide our research. I'm just looking at my notes. Yeah, and also want to say this process, I guess, of reflection and refining candidate principles should not end at this talk. We hope you take away from this that you'll do this more often with us. And also, as Vito said, the concept of using principles is not esoteric in science. It's like, a few historical examples Vito gave. So I mean, we should also in intelligence research use it. Like, we shouldn't hesitate from it. So a quick reflection of what I just said so far. So I just recounted an example where a candidate principle was useful for us, for me, for three of us, I guess, in this room, and also four. I see Nina there. We hope that you're convinced maybe just a little amount that it'll also be useful to you in general in intelligence research. And to illustrate the point, I use the illusion, but also the candidate principle of strong component interactions. Strong interaction between components. I get it wrong. But maybe you'll be more convinced that this would be a convincing principle if you see a few more examples, and Vito will take you through a lightning tour.
Yes, a lightning tour. So don't expect too much details if you're super interested in it. Let's talk about it after. But let's talk about some examples. So the first example is also from Vision. It is from my collaboration with Nico. There. And what we're interested in here really is looking at eye movements of humans in natural scenes. And based on previous research, we already knew that these eye movements are really dependent on the objects in the scene. This is also directly from Nico's previous paper, I think. And this, however, poses somewhat of a chicken-egg problem, because we also know that these objects somewhat depend on where the eye is currently looking at in the scene. So motion depends on objects, and objects depend on motion. But coming from really our candidate principle of strong component interactions, we can look at this really as two components that seem to be strongly interacting with each other. And if we implement this with interconnected recursive estimators, what we already see is that this leads us to a very good model for both these processes that is actually completely image computable, so does not depend on any pre-annotations of objects. But more details, no time. So, next example, with another person in this room, Morsen, over there from Project 27. And this really shows us that it's not just vision that we can do with this principle, the candidate principle, and also with interconnected recursive estimators, because here we look at collectives, more exactly collective estimation. And in collective estimation, really the problem is that some sort of opinion needs to be exchanged within a larger collective. And obviously, that is already very much about interactions between components, in this case, the different agents within the collective. But what we found is that if we make these interactions even stronger, following our candidate principle, obviously, by adding a dimension of uncertainty to the exchanges, so every agent communicates how uncertain it is about the opinion it's currently giving someone else, that really leads to much more complex and interesting dynamics within the overall collective. Again, no time for details. What comes next is what really this principle comes from, because, well, where does this implementation of interconnected recursive estimators come from? Well, and we are both roboticists, it might not surprise you. It comes from something in robotics. And this is really previous research to the two of us, where it was about, well, like one of the core perceptual problems of robotics. You have multiple sensors, like proprioception and vision, and you need to really solve a bunch of sub-problems to actually generate behavior. And in a very abstract view, the solution to this problem was interconnected recursive estimators, where really it is all about having these components interact with each other, which lets each component have access to much more information about its specific subproblem, thereby making the component more robust, thereby making the resulting behavior on the global system level even more robust. And this was the start of interconnected recursive estimators. As you've seen, they were already helpful to us. But interestingly, the candidate principle of strong component interaction is not just helpful to people using interconnected recursive estimators, not just to us both, but also in other implementations it can be useful. And to tell you about this, we brought you two special guests that can tell about their experience in solving the lockbox. Shigeru Sama, if you would like.
Thank you, Vito, for inviting us to represent our recent research. So in our recent integration project, we try to build a robotic system able to robustly solve this lockbox. So, this figure shows the one configuration of the lockbox, which consists of 5 joints labeled by ABCDE. And then if you want to solve the lockbox, you have to follow a certain sequence. So first, you have to open the C, push it aside, so that you can rotate the big wheel D. And only you open the big wheel D, you can slide the B to unlock partially for the target joint A. So this kind of task seems a little bit, for you, you don't have any problem to solve the puzzle after several trials. But imagine that you want to program a robot. So first, robot have a limited viewpoint. You have to detect all the manipulation affordance, which here is handles. Second, you have to know how to manipulate each component without knowing how to manipulate, predefine how to manipulate it, right? So it has to autonomously figure out how to manipulate each joint. Third, very importantly, it has to reason the interlocking dependency. So here we have 5 joints, and it's worth mentioning that if you want to solve the lockbox, you're not able to just open one lock and then exclude it. For example, for the block C, you have to first put it to the left, and then after that, put it right again. In this way, if you think about the problem complexity for agents, it has to, if you want to program an agent, and it needs 0.006% chance to solve in 6 steps. So the reasoning capability is very important. So summarize here, we program a robot which have 3 capabilities. First, detect all the vision part, and then autonomously figure out how to operate each joint without predefining. Third, it has a reasoning capability. And during the development, we figure out these 3 parts are strongly interact with each other.
So
explain more.
how we solve that problem. As every good software engineer, you would start with the basic models that would allow you to actually achieve the, let's say, minimum of the problem. So we have here the planning, perception, and control components. Of course, they need to exchange some information among them in order for them to solve that lockbox. But using just this setup, we notice it's not as flexible enough. So you would just change a little bit in the environment, and then the robot doesn't know how to do, how to solve it. So we figure out that there are actually more information that can be exchanged between the components in order to make the system more robust towards these environmental variations. So one of the things, of course, we can also forward the joint location from perception to the planning, which can be incorporated when deciding which joint to manipulate. We also notice that when the control executes a trajectory, we can forward that to perception to determine what kind of joint that is, which can be further integrated by planning to also incorporate it in the decision process. Which can be also then used to guide the control on how to do things, because if you can already estimate how the trajectory will be, that can make the control a little bit easier. So like that, adding those connections, we notice that the components are now a little bit closer to each other, such that we have new behaviors that are somehow like a little bit difficult to isolate by themselves. So somehow they incorporate the tight connection between those different components. And as you see here, these are the names of the different behaviors that emerge from this tight interaction between the components. And here you can see our system in action, actually. So this is the simplest setup with 4 joints. And you can see that the robot is trying it, it's able to solve it. Now, on the go, we add another joint without changing anything in the setup. And we also shift the position of the robot. And as you can see, the robot managed to solve the problem without any issue. We don't even need to tell the robot that there is another joint right now, or a newer one.
And I think some of you already seen this demo in the SCIoI field. So how robust it is? Of course, we have some painful data, but there's a live data for you is it haven't failed once during the SCIoI field. So we run in the system all the time, and it always succeeds because of the strong component interactions.
Yeah, that's our testimony for the strong interaction between components.
Well, thank you both. So, what have we seen so far? A little recap. We have seen that in history of science, really having principles is helpful, important to really help science progress. And we've seen that we already have a candidate principle, strong component interactions, which has been useful not just to our research with interconnected recursive estimators, but also in other implementations like the one for Xing and Tosawa. What we want to do now is actually present you 2 more candidates of principles, just with one example each to not overstretch the time and your attention spans. And we're gonna do that while populating a little table where we're gonna look at the different instances that we are presenting you and the candidate principles that we are telling you about, and really fill out which principle is fulfilled by which instance really, where do they really make an impact. And we do all of this to later in the discussion actually maybe talk with you guys about how your specific instances, your modeling experiences might align or misalign, both might be interesting, with these candidates for principles, and how your specific scientific perspective might even offer a different view, a different candidate for a principle that might really be common across many of the instances. So to start with this, let's start with the current state of affairs, which is really having these instances for the candidate principle of strong component interactions. And now we want to give you the next candidate of our principle. And here again, we want to start with a little testimonial, a little experience of having this principle, this candidate of a principle. Adrian, would you maybe please share your experience?
Share something? Yeah, so in my research, I try to equip robot hands with human-like dexterity. But even though we humans, when we grasp, for example, a paprika or a small tennis ball, the way we do that is not too different. But this is not the case for robots. In traditional robotics, you need to model the hand as well as the object in a really detailed way that the object shape differences are reflected in the commands that you in the end send to the system to grasp an object. But even though if you look at your own hand when you grasp different sized object, of course the posture that you take is different. But of course, when we do that, we don't think much about that. We simply go to the object and grasp objects of this size with ease. And in some sense, the hand, our hand, this hand, performs some of the work by simply conforming to the shape of the object. In my project, within SCIoI, we build and develop those soft hands built from silicon. And those have this property that you can simply close them, and then if you place an object, they conform to the shape of the object and grasp it without any sensing or any perception. And this observation made us think that maybe intelligence is not only located in the brain, but also in the body itself, in the hand itself. And starting from this unconventional view, we might argue that complex calculation attributed to perception and feedback control or maybe planning that you would expect happen in the brain are maybe happening in the physical interaction between the hand and the environment. And my research is guided by this perspective and the principle that falls out of that we have computation that can happen in the brain, but computation can also happen in physical matter. And now the big research question is how to now make use of the strengths and the weaknesses of those two computational paradigms in order to derive or build a really intelligent agent. Yeah. So, yeah.
Thank you so much.
Yeah.
I think you gave a better summary of the principle I wanted to just say. But maybe let me just quickly summarize what Adrian said. So, I mean, it might, the first time when you see this, like what is computational paradigm, it might be confusing, but the intuition behind it is really simple. It's that, you know, like take any biological intelligence, they don't only perform one kind of computation. By that we mean there is neural computation happening in the brain and nervous system and things like that. But there's also like other properties of the body of the hand in this case, the mechanical properties. They compute things for you, and this is not in the digital or neuronal activity sense, but a different sense. So we should really be looking at trying to solve problems for intelligence, trying to look at different kinds of computational paradigms. That's the idea behind this candidate principle. And maybe just to show off a little bit more, well, I guess you guys have seen this, Adrian is able to do incredible feats with using this principle of like letting the hand, the morphological properties of the hand take over so many things. Then you let it do the computation. You don't do the computation in your CPU or GPU. Yeah, I think there's also a strong case for Adrian being sort of inspired by and guided by the principle of multiple computational paradigm. Or also, I should say, like, when you just look at the term multiple computational paradigm, you might be thinking, wait, is it a property? Is it a principle? It doesn't really matter, like, you know, as long as it helps. So that's at the end of the day what we want to take as the view. Given this new candidate principle I just talked about, I'm just going to expand the table. So in-hand manipulation got added there, so that gets a big X, and the different sizes of X connotes different sort of fit, amounts of fit to different instances we've talked about before. I think the first three visual illusions to collective estimation, they don't use multiple computational paradigms yet, at least the things that we are investigating. But the robotics interactive perception Vito mentioned, and then the lockbox solving Xing and Osama mentioned, they also do take multiple computational paradigms into some, they leverage that principle. And I will talk about one more candidate principle, agent, environment, interaction. And this, when you just read it out loud, might seem like, well, it's a self-evident principle. Like, I mean, any creature or agent in the world is embodied, always, there's no way out of it, and it's always situated in its environment. So there will be interactions. So, but I think it is still useful for us to explicitly state this, because yes, well, it may be obvious that there is some interaction between agent and environment. it might be not so obvious that there are some structures that, that underlie these interactions. And maybe even if it is, it might even be less obvious that you can directly leverage those structures in the interactions. And to illustrate that, I'll just show you one quick example of fixation. The fixation is an act of when you're looking, let's say, at this object, and then you happen to move, but also you center that object in your visual field. You do this without even conscious notice. Like, you know, when in a train, you just can't help but look at things, keep looking at things. So this is an act that you do. I mean, you biological creatures, many kind of biological creatures do. And we can try to determine what happens if you keep doing that. Like, what happens if you keep fixating and then moving? Well, you end up tracking the trace of a circle. Now, that's a structure, right? So out of all the possibilities, space of possibilities of configurations between the environment, in this case, the environment is only one object, and the agent, out of all the space of possibilities, there's only one manifold, the circle, which is dependent on the distance to the object. So, and that's a structure. And you can directly leverage that, not by trying to go around in circles and measuring the radius, but I mean, you can do that instantaneously by simply, like you just move and then you measure the amount of rotation that immediately tells you how far an object is. So that's an example of trying to take advantage of agent-environment interaction. And so, as before, I'm going to expand the table with fixation as an instance, and that gets a big X, of course, and almost all of the last few examples we talked about do use agent-environment interaction, some structure that exists between the interactions to some extent. And eye movements, I guess, we have, like, I mean, right now it is still it's not embodied fully yet, so, you know, a smaller X, but in principle, eye movements, I guess, as we do, fast movements can take advantage of structure that emerges from the interaction. So with that, let me give you a very summary of what we've talked about so far. So in the beginning, we saw an example from history where a principle was useful, and then we also mirrored that to much less grander sense in SCIoI, and we said that it's useful for us, and then we saw other instances where principles were useful in everybody's research that we've talked about so far. And to illustrate at least the largest part of the talk, to illustrate, I used one of the principles, the strong interaction between components. And let me just quickly remind you what that is. So with this, we mean that strong and rich interactions between components ultimately express more sophistication than the components themselves. So that's principle one, candidate principle. Then the candidate principle multiple computational paradigm. Here we suggest that computation for intelligence happens in different paradigms, not just neural in the head or digital like in CPUs, but also, for example, mechanical. And agent-environment interaction, where we suggest that useful, directly leverageable structures, if we can call it that, exist in the interactions between agent and environment. And throughout this talk, again, we showed how all these candidate principles helped us, and we hope that this list of candidate principles should also apply to some extent to you doing different aspects of intelligence research, or there may be more. There may be things that we are not seeing, and there may be instances that you work on that might fit to whatever degree to the things that we talked about so far. So we will take the rest of the time today to try to discuss this, and we have, you want to do the grand reveal of the table so that we can interact with it. So yeah, with that we can start. start the discussion. Also, if you have any clarification questions, feel free to